Hello,
Hello.
Bill?
Yeah.
Yeah, I'm having a little trouble at this end. We lost our power. I was trying to log in on my laptop, but and I
Ah,
and I but I but I am on my tablet right now. I don't have access to my desktop computer.
oh, I see.
But maybe go ahead and start. Maybe I can get it to work a little later on. Maybe
Happens.
Professor Professor Cruz can talk, or maybe you'd like to start.
So far, I haven't seen um, Professor Cruz either. So you were the first one to show up. So I'm not sure of his status.
Yeah, I'm not doing the best here. I've got my tablet, but I don't see you for some reason.
Oh,
I haven't logged in
oh,
properly or something. I'm not sure
just a
exactly
moment.
what.
I think I have to change something on this end.
Oh, okay. Now I see you. Yeah.
Okay,
Okay. Yeah.
that should be better.
Yeah, that's perfect now. Yeah, we lost the power. They dug new cables under for the power, and they're changing the cables around, and they turned off our power about an
Oh,
hour
I
ago. They
see.
haven't turned it back on yet. So I'm on my laptop. Well, I'm on my tablet right now using a hotspot from my cell phone, which is pretty good. But I wanted to get on my laptop because then I can show I can share
Yeah.
screen. Well, I guess I could even do it with this. I do have the file on my tablet, but it's a little
Yes.
harder.
Yeah. In principle, it's possible. I know Jesus is doing that on occasion. I generally don't use my tablet for that purpose, but as far as
Well,
I
the
know, it
advantage
does
is
work.
the tablet, of course, has its own battery, so I'm not on. I don't have to have the house current for running my tablet, and my
Hmm,
cell phone works on its battery, so I'm on a hotspot.
right. So you're
But I'm pretty
independent of the
excited
power.
about. I think you probably got the file I sent you yesterday. I just completed that.
Yes. Yeah, I haven't had a lot of chance to read through it. I was just doing that while I was waiting here. Um, uh, you make
Yeah,
some.
somehow I think it's very strange, this set of nilpotents that the inner products all equal to 1/2. It seems to be, have you ever seen anything like that before?
No, it looks novel. The your comments at the beginning about the nature of the duality, right? That you're comparing it to so the usual duality in linear algebra um, is sort of intriguing, but your conclusion in the end that or at least in the second paragraph, you said that linear algebra could have developed from Grassmann algebra. Um, I I think is clear from the original intention of Grassmann, in fact, right? Um,
Well, yeah, I'm interested. Grossman really was convinced that his algebra was extremely important and
mhm,
fundamental to mathematics, but he was largely ignored during his lifetime. But linear algebra really developed on the basis of matrix algebra. But
yes.
what I tried to
What?
emphasize in this newest uh, file I sent you was that you don't really need to develop the matrix products. You can develop in this table 1 and table 2. Well, in fact, I studied just table 1 in this paper. And
Mhm,
all the properties of matrices really follow from that much simpler
yes.
multiplication table.
Yeah, and I think that um, hmm, well, I suppose for some reason that doesn't seem to have taken hold, but it was well known. Like it was well known at the time, you know, that a statement like that wouldn't have been controversial to anyone at the time of Grassmann himself. It's only historically because of the way that you know, Cayley and the notion of matrices and so forth historically became the preferred language. But I think it would, well, many people would be making a mistake if they equated linear algebra with matrix algebra. It's
Of course, the algebra of endomorphism.
oh, good morning, Jesus.
Good morning, all to you. We can listen to you, Professor Garret, in the past intervention.
Professor Sobczyk has a problem with his electrical power right now. So therefore, he's using a non-standard way of connecting. He's using a tablet.
Okay.
So you notice his image is a little different than than we're used to.
Yes. Okay.
He also has some difficulty to actually display to share the screen in the way that he usually would.
Well, but of course, you both have the file. I do have a copy of the paper in front of me. Well, it's a little older version, but so we were talking about just the beginning. Well, I have an introduction that I don't have that in front of me, but
if you would like, I could share that on my side.
Okay, yeah, that would be perfect.
Play with that way.
Okay, that's right. You can just display I can talk off of your copy of it then.
Sure. Yeah.
Okay.
So you just one moment here while I organize this properly.
Yeah, I see it perfectly, actually.
Okay. You notice I've already made a few comments. I would just.
Okay.
This is often what I do while I'm reading something. Is I just put some.
Okay, that's fine. So let's see here.
Marks there. Okay.
Yeah, I tried to make a distinction between I'm not saying that matrices should be in any way given up, but it's just another way of looking at the structure, how the structure of a matrix really arises in a different way, just directly from Grassmann algebra. And this table 1, this paper is really concerned with table 1, multiplication rule. And I try to introduce it on the first page of section 1. If you want to go to section 1, we can look at that.
Yes,
next page.
Yeah, I think we're fairly familiar with this now.
Yeah, but look at go up a little bit so we can see the marks, the comments I make, which you're familiar with. Okay, so that's a basic multiplication table. But I also like to emphasize right under the first nilpotents are algebraic quantities. That's a little bit up.
Oh.
Yeah, go all the way up a little bit more. Okay, right there. So nilpotents are algebraic quantities. Okay, so this we've talked about before. But the next thing that's interesting is the second point. A set of nilpotents, A1 up to AN, is multiplicatively uncorrelated if when you add them together, you get 0. And of course, that of course defines the Grassmann algebra part of the linear algebra. And of course, then I'm introducing in equation 2 the fact that the outer product in Grassmann algebra is not equal to 0 as a characterization of linearly independence. Okay, and now we can go to that table 1. So what I'm emphasizing is that linear algebra can be built on. So you see, I'm not even introducing. I'm saying, okay, and I define the second asterisk, or a set is said to be positively correlated if the sum is equal to 1. And of course, that's something like a statement of duality in the usual sense, but then I had a distinction in my introduction that it's not really, it's closely related, but it isn't the same thing because it involves really a geometric algebra in the process.
Mhm. But for me, this statement 3 does something a little bit unusual. Like in particular, it introduces this
Yeah, I define
operation.
what a null vector is here. At first, I define a nilpotent, but then I say a null vector are really the basis of the Grossman algebra.
But
And then I introduce this
but
idea
in
of
statement 3,
correlation.
you've introduced an inner product, right?
Well, that follows from the symmetric, since they're correlated, that follows from the definition of what I mean by correlated. Forget the negatively correlated, just think about positively correlated right now. So that's just saying it's equal to 1 minus the delta function. So it preserves the Grossman structure, but when they're correlated, then you get 1/2. Well, between two distinct pairs of these null vectors, all the inner products is equal to 1/2, defined by that equation.
But so far, but up to this point, you only referred to vector space. You didn't presume
That's right.
anything
I'm
about
defining what a
metric.
null vector is. I'm defining what a null vector is, namely they're elements of the generating the Grossman algebra if they're uncorrelated. But if they're correlated, then you have additional,
Yeah,
then you
yeah,
have
no,
the symmetric product.
that's entirely clear. The issue for me is that as soon as you introduce this
Take that as a
dot
definition.
product, but the dot product doesn't belong here from my point of view, right? I mean,
Well, I'm defining it in terms of that symmetric product.
you mean
That's really a definition. Define the inner product equal to AI AJ plus AJ AI. Definition.
oh, but
And that's of course the Clifford algebra structure.
Mm. But suppose we had a Clifford algebra with some other metric. In fact, you were talking about Minkowski space, and Minkowski space, has a specific
That's what
metric.
I tried to point out in the next couple of pages, that this set of nilpotents, correlated nilpotents, as I call them, define the geometric algebra of a Minkowski, Lorentz Minkowski space with metric 1, n.
But the definition of nilpotents requires definition of product before.
Well, I use if they're uncorrelated, then that just means they're anti-commutative. And in that case, they generate the Grossman algebra. But now I'm saying they're correlated, and that's where I'm defining the inner product equal to the symmetric part. Well, the anti-symmetric part is still the structure of the Grossman algebra, but the symmetric part well, first of all, they're all nilpotents, and now the symmetric part defines the inner product. Well, I define the inner product in terms of the symmetric part, which means that I'm calling that to be a correlation between distinct nilpotents. And those nilpotents actually generate the Lorentz Minkowski space or Clifford algebra 1, n. you know, the standard basis of that algebra is just E1 squared equal to 1, and then F1, F2 up to Fn squared equal to -1, and they're all anti-commutative. That's what defines the Clifford algebra structure then. And now I agree the multiple the idea that all the inner products is equal to 1/2. The calculations can be very tricky, and for the most part, I left them all out because I haven't really. I spend a lot of time on checking these calculations. That it can be very confusing, but I think everything I'm saying is consistent, and I've tried to indicate the calculations in some cases, but in many cases I've just left them out. Like for example, how did I find that the definition of the standard basis of the Clifford algebra 1n, the geometric algebra 1n? That was extremely difficult. I spent a long time before I came across this, what I call a canonical definition of these of the standard basis of the Clifford algebra in terms of these nilpotent vectors, which is it's all very.
Maybe I'm just
Go ahead.
distracted by this point. I don't know. I would really like if you would just like just leave that out. you know.
Well, take that as a definition. That's all I want to do with that. It's a definition. It's equal to put that first before the AI AJ plus AJ AI. Okay, put that first.
But do we need this dot? Like, do we need dot? Like,
well, I'm just defining it. Well, that's right. I don't really need it, but the famous thing about the geometric algebra is that you define A dot B plus A wedge B. That's the geometric product. So really, that's coming in there. So, for example, with the AIs, you get AI dot AJ. They're all equal to 1/2, but the AI wedge AJ, that's equal to a bivector, just as well in the Grossman algebra.
But
so again,
suppose we had like a curved space of some sort, that in which the metric was not Euclidean, but just something more general.
Well, that's right. That'd be the tangent space then. Well, that's right. I haven't really. There's no reason why. Like I say, basically, I'm trying to show here that this is just another basis for the geometric algebra 1, n, but it's an interesting basis in that it has, all the inner products of these basis elements are equal to 1/2, which is pretty strange, really, when you think about it. In fact, you can see what that means in, for example, in 3-dimensionals or in space-time. You can define 3 null vectors, just all the inner on the light cone with 120 degrees between each pair. I guess that's right? So if you increase the number of dimensions, you can still keep that unusual property that all the inner products of these nilpotents is equal to 1/2. With 2 dimensions, it's easy. You just, the nilpotents are just on the horizontal, the light cone, the usual light cone. In 3 dimensions, you'd rotate that light cone and you define an ice cream cone, and all the angle between all 3 vectors is 120 degrees, with the inner products equal to 1/2 between any pair of them. And then you go to 4-dimensional space-time. Well, in fact, you can go to n dimensions, and you can keep those inner products on the light cone of those higher dimensional spaces are all equal to 1/2, which is rather surprising, really. It seems like. And it seems like quantum mechanics. I try to point out where I think quantum mechanics might arise, just in the fact that all the inner products of these of these nilpotents are equal to 1/2. And of course, 1/2 is the usual half spin. And you can define the other spins in terms of course, multiples of a half, which seems to, well, so also in quantum mechanics, a quantum state can be represented as a nilpotent as well. So anyway, or an
Okay,
idempotent. Idempotent. And of course, the interesting thing is a product of these two distinct A1 times A2, that's an idempotent. You square that, it's equal to itself. All those properties follow from that basic table 1 that you have on the screen now. AI times AJ times AI times AJ is equal to AI times AJ. So again, all the basis elements are nilpotents, but take a product of any pair of them, they're an idempotent, which is unusual. Doesn't matter what pair you pick, which is strange. Anyway, I've tried now to develop the calculus in this particular paper instead of using the Euclidean definition of the gradient or Laplace. I use the Laplacian Minkowski space-time to define the gradient, or what we call the vector derivative. But that's consistent with the Dirac algebra. You know, the definition of the vector derivative in the Grassmann algebra is exactly the same as in the algebra on the light cone now that I'm defining in for the Clifford algebra 1, n. Anyway, yeah, go ahead.
Okay, maybe I've lost the thread a bit again, but here suddenly, like you've introduced, Grassmann algebra 1, n. So the 1, n is what you would mean by being Minkowski, right? I guess
that's right. So that defines the 1, n is where you have one vector with positive square, and all the rest of the vectors have negative square minus 1. That's the standard basis of the geometric algebra 1, n, which I call Lorentz Minkowski space of n-dimensional, n+1 dimensional space. And you could equally well define that picking out a set of null vectors whose inner products are all equal to 1/2. And I give the relationship between the two bases in that table that you might want to skip to that table.
But let me ask this question. Suppose we weren't interested in like 1, n, but rather say 0, n, but we still wanted to use null vectors to represent it. Like, so just a standard Euclidean space, not a Minkowski space, but just an n-dimensional.
That's just the Grassmann algorithm without a, if you don't have correlation between these null vectors, and it's just Minkowski, or it's just Grassmann algebra. And of course, in Grassmann algebra, each square vector, they're all null vectors because they all.
But I mean the Clifford algebra, or Clifford geometric algebra 0, n. So it's Euclidean geometry, but with the Clifford structure.
Yes, exactly. That's right.
So how do we generate that?
Pardon, what was that?
How do we generate that with null vectors?
Well, for example, that's if you take a set of well, as I do it here, of n+1 null vectors, and you take just the outer product of those null vectors, then you have exactly the Grassmann algebra. But now I sneak in, by this idea of correlation, I sneak in the inner product all equal to 1/2. as a symmetric part of the Clifford product. And that's in number 3, equation number 3. Forget, as you say, you don't have to define that A dot B there or A dot A. Just keep it as a symmetric part. So the inner product, that's just an abbreviated notation for the symmetric part of the Clifford product, which is
Okay.
VW plus WV, and then VW minus WV is the antisymmetric part, which defines the Grossman algebra. Now, later on in the paper, I find that actually, if you modify that inner product just a little bit, then you can get the standard basis of the Euclidean space, which is, there are a
Okay,
lot of
that's,
strange things that happen, it seems like.
Okay, let me let you go ahead with that and stop asking questions for a moment, because that, if we can get to that part of your paper, then perhaps it answers the question that
All right, let's go on to the next page then. You can
Okay.
see the
all right, so that's
okay, we can forget about the negative correlated ones there. I'm not interested in that here, really. So keep going to the next slide. Oh, okay. Well, okay, look at that definition for alpha K. Go up a little bit more. Well, I don't want to talk about the negative. So let's, look at equation 4 here. Okay, that's a good equation, because you see, first of all, I define that AK as just the sum of A1 plus A2 plus up to AK. So I'm defining now the standard basis of the Clifford algebra G1n, Fk equal to alpha K times AK minus K minus 1 times AK plus 1. So I'm defining all the elements of the geometric algebra of Minkowski space-time, or Lorentz-Minkowski space, for the general geometric algebra with that metric, in terms of the null vectors, all with inner products equal to +1. So this was extremely difficult for me to find that. In fact, I managed to find that formula, alpha K, just by calculating higher dimensions until I saw what the relationship was. But so a more thorough description of this would actually be to show exactly that all these relationships indeed generate exactly as I claim they do, I haven't really given many calculations here. I just wrote down that relationship. I know it's true because I've worked through it many times. Like I say, some of these formulas, it's very confusing to have all the inner products equal to 1/2. Anyway, you can see that number alpha K is very important because it defines the general standard basis of the geometric algebra 1n as a formula, recursively, really. Okay, so you can skip the next one. That's the negative correlation. So again, we're only assuming the multiplication rules given in table 1 define follows from the multiplication table 1 and this definition of correlation. Well, actually, table 1 follows from the definition of correlation. Yeah, so the way you should think about it, the correlation idea is the basis for everything. The table 1 follows from that definition of what we mean by correlated null vectors. All those rules follow from the table 1 follows from that one basic definition. Nothing more.
What's the symbol, capital A here that I've highlighted?
Okay, let's go back up a little bit. Keep going. Keep going. Keep going. Keep going. Okay, right there it is.
So it's partial sums of the A's, is that?
That's right. Yeah, so A n plus 1 which is kind of like a a pseudo-scalar element. That's the thing. It's an add. It behaves like an additive pseudo. You're defining. That's the strange thing about this. It's like a pseudo-scalar element, where instead of using the outer product to define the pseudo-scalar element, you're using the sum of these nilpotents. So an plus 1 is a very basic element. And when you look at the algebra, what I call an plus 1 script, that's really another representation of the geometric algebra 1 comma n, which is pretty strange to me. Okay, so we can go down, you can go a little
Alright.
further, we'll see how it works out. Like I say, I don't really spend a lot of time trying to prove any of these statements, but I try to give an indication. Okay, so there you have table 1, very important. Okay, keep going. Okay, there you have the definition. It doesn't matter whether you're using table 1 or table 2, the alpha k stays the same, no change really, which is interesting. Okay, so go on, we'll go to the next page now. Oh, by the way,
Okay.
you can see the notation I'm using here. Gn, well, okay, Gn1, I'm extending the real numbers by these. So I'm thinking about extending the real number system by these nilpotent elements, nilpotent vectors, really, null vectors. But the definition, again, 5, that's a negative correlation, is the same as with the same alpha k. That's not a misprint. It's exactly the same as in the previous case. But I don't want to consider the negative. It's bad enough just to think about the positive correlated. You don't have to worry about the negative correlation. But it is interesting because of the relationship to Clifford algebras. Okay, so go on to the next page, please. Okay, now this is important because it relates to the standard basis, E1, F1 up to F7. So that's the Clifford algebra G1 comma n, and so then the null vectors A1 up to A8. So that's I write it as 1 plus 7, or n plus 7 plus 1 is A8. So again, that consists, so the standard base is just E1, F1. These are orthonormal vectors in the standard basis. Now you can relate this basis to the basis of all the inner products equal to 1/2 of these nilpotents by this matrix, which is pretty strange the way it looks. And then, of course, simply taking the inverse of T8, you go down the screen a little bit, you can see what the inverse of that matrix looks like. So we'll go down a little bit more. And there's the inverse of the matrix there.
I was just going to point out one thing that you've discussed before, I think, and that is that this and how should I write this here? Just a minute. If I do this differently, if I there was this. Come on, draw the line. Oops, sorry. I just wanted to.
Okay, yeah, you have more.
Oh, I was trying to draw a line here. Sometimes it doesn't work quite the way I expect.
That's fine. I see it. I see the yellow.
Yeah, it was.
That's right. So that's telling you that E1 is equal to 1/2 A. No. That's relating the. Yeah. No,
Well,
yeah. E1 is equal to A1 plus A2. That's what that first line of the matrix T8 is telling us. And F1 is equal to A1 minus A2. And that's what I call the, what I call them the key That's defining E1 and F1. Those are the, I think I call them, what do I call them in the paper? I think I call them the key elements or something like that. I forget.
So the relationship between the first two elements seems anomalously different than.
Yeah, that's the G11. So those two elements generate the Clifford algebra of neutral signature G11. E1 squared is equal to 1, F1 squared is equal to -1, and E1 and F1 are anti-commutative. All that follows from table 1, the multiplication table 1. Okay, that's the simplest case. And then you extend it by adding these other F's and F1,
But as soon as
F2.
we go to 1, 2, then it no longer looks well.
That becomes a complex Clifford algebra, 1, 2. And that's like G3. G3, if you reinterpret those elements, that gives you the geometric algebra of Euclidean space, and the pseudoscalar element behaves like I squared equal to -1.
But then, as soon as we go to 1, 3, like something quite strange happens, right? Oops, sorry.
Yeah, exactly.
Again,
That's right.
like the strange thing the thing that seems strange to me is this sort of sudden appearance of this.
Yeah, it's very strange. I agree with you. I worked a lot, I had a lot of trouble understanding this stuff. It just seemed like it was impossible, really. I spent, anyway. And I had to introduce all kinds of new notation, which is strange too, of course.
Geometrically, it looks like if you will one element of the base, adding two of them, the first two of them, and then getting the subtraction with the third. Then I think in the previous definition of for a capital A, you are adding all the elements until the K term. Okay, here.
Yeah.
And after, if we go to the next page, please. Okay, here is the definition. Then if we take a capital key, then you are taking something like the diagonal of this subspace. And then you are subtracting the next nilpotent, and then you get one kind of orthogonal to this nilpotent K plus 1.
Right.
I think that this is the geometric interpretation of this new base that you are building. And then in the matrix notation of the transformation, we can find the first all zeros because they are that subspace are orthogonal to this new one.
That's right. That's exactly right. Yeah, you can see that those first two elements. After that, the matrix is diagonal. That's the only thing, that extra one there prevents it from being a diagonal matrix, but it is very important. And that really defines all the I don't think there's any other way of defining the other elements. But that's the thing, all these vectors are mixed together, but that null vector basis, all the inner products are equal to 1/2. So you can rearrange them in any order you want. The fact is you can pick out any F1 and any E1 and F1 to be any of the, and then redefine the whole basis. But that's why this n plus 1 is important. It's behaving somewhat like a additive pseudoscalar instead of a multiplicative pseudoscalar as usual in Grossman algebra. Let's see. Let me let's see. Let's see. Maybe go on to the next page. Maybe I can see something. Yeah. Yeah. Go on. Keep going down a little more. Okay. Now I want to define the gradient operator. And okay, go down a little more. Okay, here. Stop here for a second, if you would. Now you can see what I'm doing here. Given any two distinct AIAJ in this algebra of nilpotents, define E equal to AI plus AJ and F equal to AI minus AJ. So that's just like using A1 and A2, but we're using it, take any two of them. It doesn't matter which one. And now we can actually see the calculation. From table 1, if you just look at E1, E squared in equation 6, you can see I'm multiplying it out, very simply done. And of course, since they're nilpotents, AI squared is 0, AJ squared is 0, and you're left with AI times AJ plus AJ times AI equals to 1. Well, that's good. That's a unit vector. Now look at AI minus AJ times AI minus AJ, and you square that, you get -1. And then you can easily calculate, again, all these 6, 7, and 8 are following from the multiplication table 1, nothing more. So in other words, what you assign as a vector, no, it's very strange because it puts all these things on the same level. All the inner products of these basis elements are equal to 1/2, which, well, in quantum mechanics, particles, if they're entangled, they're indistinguishable, or bosons, you have plus 1/2 and 1, all indistinguishable. Well, okay, all these nilpotents are completely identical. But what's a vector and a bivector and all that? Well, actually, that's unique too, but they're all defined in terms of these null vectors. Anyway, so 6, 7, and 8, I actually go through the calculations. They're very simple. You can see that they are, and they all follow from table 1. Okay, now the gradient operator.
But one point you just made sounds quite interesting, that one thing that we sort of obsess about sometimes is the grade of the object. So we talk about bivectors and trivectors and so forth, but you just made an interesting statement that I think that in the basis you're discussing, you don't make that distinction in the basis of the algebra as such, right?
That's right. In fact, all these elements are nilpotents, and you define these elements which have square 1 or square -1 in terms of these nilpotents. All of them. But in a way, you can do it in many different ways. What you call F1, F2 in one space, well, it becomes more complicated as you add dimensions, but you can pick any order of the nilpotents in order to define it. In other words, anytime you talk about any two of them, the product of any two of them really determines the whole structure of the algebra. Any two distinct elements. Well, okay. So in number 9, you can see the equivalent of the Dirac operator. The way it's usually defined, you probably recognize that. That's usually called the D'Alembert. You have the gamma 0 would be E1, and gamma 1, gamma 2, gamma 3 will be the Fs. Okay, so that's like the D'Alembert defined in terms of E1, F1, F2, F3. And of course, for G1n, then you just extend the idea, but it's still a Lorentz-Minkowski space. Okay, well, you can go down a little further if you like. Okay, now you can see what I'm doing here. Stop at 10 there. I'm defining the standard basis, a position vector X. I'm using the position vector in the standard basis of the geometric algebra, Clifford algebra, to be S1E1 plus SI plus 1 FI, and so on and so on. That's usually the standard basis, okay? But for the nilpotent basis, I use, okay, that's just notation. But again, then I have the matrix of transition, which I defined earlier, apply then to go from the standard basis to the basis of nilpotence then.
So this notation S, is that?
Yeah, that's just with the standard basis. I use just X1, X2, and so on in the basis of nilpotence. So that's just, but again, you can represent it, the basis elements in either in the standard basis or in the nilpotent basis. It doesn't matter which one. With the matrix of transition, I give T8 and T8 inverse. But I don't really, I did that in the other paper. I'm not really trying to do those things here because that was in you can find that paper on my website or on my ResearchGate. I published a lot of the preprints of these things of my struggles. I probably shouldn't even put them on my ResearchGate page, but I didn't publish it as well, I think I called it a preprint, but it's not really even a level of preprint. It was just calculations, trying to understand this stuff. I've left the earlier versions on there because to understand this, it was very difficult to come to understand what's going on with these nilpotents.
This notation S though, is that maybe did I miss that? Are we defining it above somewhere?
No, I never used it before, but you see, that's what takes you from the basis of E1, F1 up to Fn to A1 up to An plus 1, you see? So that does relate those two bases then, you see? So if you write I write the position vector in the standard basis as S1E1 plus S2 F1 plus F3 F2 and so on. That's the standard basis of the Clifford algebra. But if I take the other bases, I write it as X1A1 plus X2A2 and so on in the standard basis then, or in the basis of nilpotence. Okay, and the relation, again, I relate those bases right here. So you can see. I'm trying to keep things as simple. Okay. Yeah, that's the standard basis of the Clifford algebra. And that's relating these two bases. That's the basic relationship between these bases then. So I'm not trying to prove any of that.
That S subscript 1 is the same as F1 and that S subscript 2 is E1?
Well, it's that Gn comma 1, that's where I'm looking at the negative correlated one. So I'm not using that at all now. 1n is, I'm not changing notation there.
But this, so here in 9, you wrote partial S sub 1.
Yeah, that means partial S sub 1, that's right. The partial derivative.
But what is S sub 1?
Well, that's really partial S1. That's an abbreviation for the partial derivative with respect to the variable S1. That's the, the position vector is S1, E1, S2, SF1 plus F. It's a little confusing because of the notation. I should probably use E0, F1 up to Fn, but I started out that way and it just became impossible to change it then. So you can see 10 gives you the standard basis then, S1 E1 plus SI plus 1 FI. That's the standard basis of the geometric algebra. Well, position vector for the Euclidean. Well,
I'm sorry. Okay, so S1 is just a scalar value of some sort.
Real numbers.
But then you are considering defining a metric here, because you are building the position vector like a linear combination of the bases multiplied by elements of the scalar field.
Yeah, that's right.
But then there is a metric defined in it, and I don't get to find where is that definition before.
Well, that's the definition of the Clifford algebra. Maybe you can go back up. I do define the Clifford algebra above.
Then you are supposing that the Clifford algebra have implicit one metric definition.
That's right. That's the standard metric of the Clifford algebra. But all I'm doing is introducing.
Then we can don't get a Clifford algebra without a metric definition before.
That's right. I didn't. Well, I did mention the structure. I said that E1 S squared plus 1. They're all anti-commutative vectors. E1 plus 1, Fi equal to minus 1, and they're anti-commutative. So the Grossman structure is the same, but it's the inner product which determines which geometric algebra we're talking about. But the thing is, with the A's, it's like we're replacing, instead of the pseudo-scalar element, we're using a dual sum scalar, because of the nilpotents have square 1/2, have square 0, but the inner products are all equal to 1/2. That kind of really uniquely determines the metric on the space in a way. That's what's happening, because the AIs with nilpotents with that correlated relationship determines the structure of the geometric algebra, 1, n. Which is unusual, I guess. I have never seen that before. But it's anyway. Okay, so let's go on. You can see the other okay, here I try to characterize the gradient operator or the vector derivative in terms of two properties. One, the gradient operator has properties of a vector. Okay, so I use X as that vector. I'm introducing the notation, all vectors in the geometric algebra GPQ1, that means vectors. Okay, it's a graded algebra, and of course vectors are the bottom. And then if you take the gradient of X, it defines the dimension of the space, P plus Q. And of course, why we have that, that defines it. So it doesn't matter what metric you use, the gradient of the position vector in that basis will always give you the dimension of the space. Okay, well, I'm not really interested in PQ. Uh-huh.
Didn't
Oh, and
you all
two, the
make an
directional
assumption
grid.
about the metric though? In
Well,
10?
that's, whatever it is, then I define the grid property. That the gradient of the vector gives you the dimension of the space. And if you take the dot product of a vector with the gradient operator, apply it to the position vector, it's the identity vector. It just gives you back. So that's like, if you define a dual space to be the space of both forms, people use covectors and all that for the dual space. That's really where I'm encoding what's usually defined in terms of the codes. Instead, I'm defining it by these two properties instead. But of course that was, and I make a note that is exactly what I did with the Euclidean metric when I developed the properties of the gradient operator as a tool for linear algebra. That's what I used in my doctoral dissertation. But here I'm pointing out that it doesn't really matter what metric you use. You can still define the vector derivative in a way where the metric is not important. It's really the concept of duality that's important, which people usually define in terms of the dual space, which is dual space of covectors. But really, this opens up the possibility of defining the dual space in terms of the sum of these nilpotent elements, because the vectors of the bases are all nilpotents. There's no distinction of the metric, but only in pairs of vectors you get the distinction of all the pairs of vectors have inner product 1/2 as reflected in the relationship AI times AJ plus AJ times AI is equal to 1 for distinct I and J. So that allows you to put the structure of the dual space as a sum structure rather than, which in a way simplifies things, but it's completely different than the usual way of looking at vectors, bivectors, trivectors, and so on up to n plus 1 vectors. And anyway, I try to do that, and I do mention that I'm doing what I'm doing with Lorentz-Minkowski metric, what I did with the Euclidean metric as a tool for linear algebra in my thesis, which was criticized. In fact, this book with Hesnes and myself, people always criticize it because you're introducing a metric on your matrix algebra where matrix algebra does not have any metric. That was always a criticism of this vector calculus, vector manifolds. They did not like the fact that we've introduced the Euclidean metric as a tool for linear algebra, because linear algebra, there is no metric inherent in the definition of a matrix. Well, I'm showing that really that's correct with this definition as well by these two properties. So the vector gradient, doesn't matter what metric you use, the properties of the vector gradient is independent of the metrics. So that's the whole idea of 11 and 12, and that you see on page 5 there.
But could you repeat again what you said about covectors?
Okay, so usually, of course, a covector is defined by a functional, right? If you take a standard basis in geometric algebra, then the covectors all map to the inner product is equal to delta ij in the covector space, right? So that's really imposing Euclidean metric right there, the way if you look at it. But in fact, it can be any metric, and that's what's different in this treatment here. The fact that you choose the inner product of all these null vectors equal to 1/2, the metric comes involved in the relationship between any pair of vectors. And since the null vectors all have inner product 1/2, that's really allowing you to transform a dual vector from a n+1 vector into a sum. That's what the capital A n+1 is. It's a sum of A1 plus A2 plus A3 up to AN+1. It seems to me that's what's going on. In fact, well, again, we'll go on and I can show you more things, what happens when you do that. So if you
Well,
go to page,
I'm still
okay,
still a little bit confused though by what you're saying about covector. So
how do you
in
define a
Grass-
covector?
in
Tell me what a
Grassmann algebra,
covector is.
with Grassmann algebra, as you said, we would have a, a vector space and its dual, and the covectors would be in the dual space.
Yeah,
And
that's
we would
functional.
have
I'm mapping each
but-
vector. Yeah. Mhm.
But the critical thing is that we have another operation called insertion, right? That we can take an element from the vector space and insert it into an element in the covector space. And the result of that insertion, say, of a vector into a one form, or like one covector, is a scalar value. But we don't call that a metric as such, right? Because the insertion operation is between elements of two different kinds, right? Like one is a vector and the other is a covector.
Okay, and that's the difference here. In this, the way we're looking at it with this symmetric basis of A's, you're not in other space, you're in the same space really. But you're saying the null vectors are correlated positively. All the correlation being this AI AJ plus AJ AI equal to 1. But you can see that's very close. The only difference is if you just took AI parentheses AJ equal to delta IJ, then you get the standard basic definition of a covector. So you can see it's really pretty closely related. So you're just introducing, the standard way introduces a functional on the vectors, and functional space is called covectors. But here,
Yes, I think for me, this is a critical point. And I think it would be beneficial in this paper if you could spell that out like in some detail, at least for me, right? Because
okay, no, I think it's correct because everyone does it that way. And that was the main criticism of this idea of a vector manifold. You cannot use a metric in a metric-free space of linear operators, basically. But I'm trying to point out here that that's not really an important idea.
But
You can-
if we go to the standard definition of vector and covector, then we need to find how we transform, for example, the x position and the gradient operator. How is defined here the transformation ruler in this? Because if we apply a gradient operator to x position vector, then we get one scalar n+1.
That's right, counts the dimension of the
Then
space.
in any kind of transformation that we use here, we need to know how is transformed the vector and how is transformed the gradient.
Yeah,
In the way that the transformation of one scalar take to us to one scalar again. No?
okay.
And then those this take to us to the definition of vector and covector.
Okay, well, let's go on and maybe some of these ideas will clarify themselves as we go on.
okay.
If we can go on a little bit, maybe we can come back to this then.
Okay.
Okay, look what we have here now. Okay, so this is again Okay, so the gradient operator behaves like a vector in the space. So if you take the divergence of it, it's like in Gibbs Heaviside vector algebra. That's where I started with this idea is in Gibbs Heaviside vector. You can think about geometric algebra G3 as a generalization of Gibbs Heaviside. And of course, the gradient operator, the divergence of the position vector is equal to the dimension of the space. Well, in this case, that was when n is equal to 2, then we have G3 then. So, and the curl or the cross product is equal to 0. So those are well-known properties. The gradient operator in Gibbs Heaviside, the dot product divergence of the position vector is 3, and the curl of x or the cross product is equal to 0. Okay. So that's okay. And if you take the dot product of the gradient operator in Gibbs Heaviside with the gradient operator, apply it to the position vector, you get the, so those are where those rules come from, simply from Gibbs Heaviside vector algebra, which is universally used for engineering courses. It's still, well, now they use a little more differential forms, and they sneak these ideas in, as you say, covectors and so on. But really, the success of Gibbs Heaviside has been due to the fact that you have a dot product and you have the cross product. Well, then they relate it to the Hamilton's quaternions and so on. But anyway, you can do it anything. Okay, but now let's look at 15. Okay, so here I'm introducing a new gradient operator, which I'm calling the null gradient. So this, I put a hat on that. So the gradient with a hat over it means AI partial I. The position vector, okay, 16 defines the position vector in terms of this basis of null vectors. Okay, so the position vector is just xi ai, I equal to 1 to n plus 1. And that's in the algebra of nilpotents, which are positively correlated. That is really another definition of the geometric algebra G1n, but it's using this basis of null vectors. And null vectors are correlated in the sense that AI times AJ plus AJ times AI is equal to plus 1. And that's the same thing, that's equivalent to define the inner product equal to 1/2. Okay, now, again, covectors. Usually covectors define as a functional of the space of covectors of what? You know the definition better than I do. F of AI is equal to delta ij, right? It gives 1 on the vector and 0 on all the other vectors. But that's like the Euclidean product in a way. But okay, let me just talk about these gradient operators here. Okay, so you can see that's a new type of vector operator. Okay, it behaves like a vector because, okay, so look at, again, 16. 16, what I'm doing is I'm just saying xi/ai. Okay, and now I'm defining the sum gradient. Okay, the sum gradient, instead of using a hat, as in 16, I'm putting an upside down caret. And that's where I define AI caret as again, an plus 1, that's like the pseudoscalar element, additive pseudoscalar, if you want to call it that, minus AI. So that's kind of like a dual operation, right? Except it's a dual sum operation. Okay, so I'm defining that gradient as a caret where I'm defining that notation, hat, and I give you an example because it's new notation again that I need to introduce in order to talk about these things by the structure of it. Okay. Okay, now if we go down to 18, we can put those two to, okay. Notice what I'm doing here. 18 I define a sum partial derivative operator. And I call that gradient parentheses n plus 1. It's just the partial with respect to x1, partial with the sum of all the partial derivatives. In a certain sense, that's like a trace operator in standard linear algebra. You can think about it that way. Okay, and now I start developing some of these formulas here. If I take V dotted with an plus 1, so remember an plus 1 is the sum, a1 plus a2 plus up to an plus 1. You dot it with that, what you get is I equal to 1 to n plus 1 of n over 2 times vi. And I notice I'm defining vi caret, and now you have to go to the, okay, now I define, I mentioned my footnote there, but we can go to the next page now. Okay, stop. Okay, so again, I'm defining caret of a vector as a sum. Again, that's like an n plus 1 vector is the pseudoscalar of a geometric algebra. Well, you can think v caret is like a dual sum type operation. It's just the sum of all v1 plus v2 up to vn plus 1. Now, if I take the caret over the, remember the vi are all real numbers. Okay, they were a vector v is equal to v1 a1 plus v2 a2 plus v3 a3. So that's the vi's are real numbers. Don't forget that. Again, notation, I agree, is a little bit confusing because, well, I had to do something with it because the usual notations are too clumsy. For example, v hat, caret, call that a caret, is I equal to 1 to n plus 1 of the sum of those components with respect to the null bases of nilpotents. So if I say v caret I mean leave out the ai. Because remember, all the inner products of the ai is 1/2. So, but that, anyway, it's kind of making the sum neutral operation in a certain sense. It's like the pseudoscalar element, which again defines a dual element. If you look at it, going back to the covector, the pseudoscalar element plays a duality role between a covector and a vector in Clifford algebra.
I'm a bit confused by your statements just now about vi being a scalar. I don't.
Okay, let's go back one slide so you can see the notation where I introduced it. Okay, go back a little more. Okay, there's a position vector x. X is equal to xi ai. I equal to 1 to n plus 1. Okay, so a vector v, let's see where I define my vector v. Let's go down a little bit. Okay, there's v. Okay, here, v. Here's v right here. V is equal to scalars. v1, these are real numbers. v1, v2 up to vn plus 1 are all real numbers. Okay. But that's the thing, that's a little confusing notation because I introduced v caret as just the sum of the coefficients, not as, that's confusing. I agree the notation is confusing right here, okay? So the v hat is the sum of all the v's. That's like a dual. Well, in a certain sense, you can think about it as a covector, really, right? Well, not really. But that's made possible because of the strange property of these dual null only pairs of only the inner product of pairs of the vectors is defined to all equal to 1/1, which is the unusual property of this whole algebra. Okay, well, now you can see relationship 20. If I take, remember the partial parentheses n plus 1 means the sum of all the partial derivatives applied to x. Well, that partial 1 of x is a1, partial 2 of x a2, and so on. All other partials are 0. So if you take partial n plus 1 of x, you get an plus 1. That's kind of like a covector in your dual space because it's taking a vector into the dual element n plus 1. So what I'm trying to say is that you're getting the same structure of your vectors and covectors, but in a different way. But it's really equivalent, but it requires different notations and different way of thinking about it because, well, that's what I have to make clear and I'm trying to make clear the structure of the gradient operator here to try to understand it better. Okay, anyway, 20 is an important relationship because that says, remember, partial n plus 1 means partial x1 plus partial x2, all the sum of all the partial derivatives. You apply that to x, well, you get the vector back, an plus 1, which is like a dual or a pseudo scalar, but it's a sum, not a sum is really, you know, in representation theory, the way representation theory is developed, it's all developed on the basis of covectors and all that. But really, this might offer a different way of, hopefully a more simple way, but I don't know, a different way of approaching representation theory, for example. Okay, notice now in 20, we have an plus 1 dotted with this, that was the hat gradient operator. You get that equal to n over 2. So again, this is a kind of a relationship between the scalar sum derivative, partial derivative. I'm looking at 20 here. Oh, okay, v is a vector. The dual is a scalar, very important. Whereas both vi and its dual
but this
are
notation,
scalars.
this notation here, very still, I'm a little struggling with this. You said caret v sub I, but v sub I is a scalar.
So, yeah, that's right. That this notation is because these are scalars. That's like a dual covector type idea.
But here,
because I'm defining it only in terms of the scalar.
But what you just written here in 19, what you've written in 19, like v sub I, is no longer a scalar in the second part.
That's right. No, it's still a scalar. You can see I'm adding the coefficients, but I'm leaving out the ith coefficient. So it's the scalars.
But it's
the scalars.
But the ith, you just said ith, right? But if vi is a scalar, then I'd say, okay, well, pick the scalar 3, for example. Then what is caret 3? Like, I don't.
Okay, what's confusing
so
is
the
because
I is important.
The previous slide I used. Yeah, I could have, maybe I should have put the caret over the I, maybe. Well, no, because then, okay, go back where I defined V again. Let's go back to the previous slide to see the V again.
Well, no, I think maybe what you might say is something like caret of V.
Because I said the caret of.
I think that it is needed the definition of vector and scalar, because here I understand VI invert the hat like a vector, because it's a linear combination of vector. Then I don't know how these go to a scalar.
Yeah, it's just a definition. That's why I put the 2 dots there.
But
I agree, the
then you are
notation-
now defining the scalars in this expression 19.
Yeah, yeah. If we went back, if I use that caret over an A, if I said caret AI, I meant A1 plus A2, leaving out the AI, which is a vector. But here, I'm thinking, yeah, I agree the notation is not good, but you know, I agree it's not good, but I'm defining it that way, unfortunately, because I didn't see any better way. But so it's an abuse of notation. I have abused notation. It's a sin. I know it's a sin. But
Okay. It's only not so much a sin, but maybe a barrier to understand what you're saying.
yeah, well, that's the thing. But if you just clutter everything with notation, that's a sin also, because you can't understand anything then. So I hope this is a lesser sin than trying to make the notation unambiguous and that nobody even wants to look at it because it's just, just symbols all over the place. But okay, so again, here I haven't tried using a caret here. I introduced, just like I said, like here with an plus 1. Notice when I use a parentheses n plus 1. No, I don't. Yeah, I don't use that. You see, that's again a little bit note. So an plus 1 means a1 plus a2 plus an plus 1. And okay, so that's a little confusing there because I never use the notation a parentheses n plus 1. Okay, that's confusing too. So, okay, but look at the next equation. Anyway, I'm just trying to develop these formulas here. Okay, look at this formula here. If I take partial n plus 1 x an plus 1, then I get, that's the combination of n plus 1 things taken 2 at a time. N plus 1 times n over 2. And if I take, again, I'm just developing some of these formulas to try to nail them down. It's okay, but 21 is an important formula because if it says if you take the gradient caret plus gradient hat, you get an plus 1 times partial n plus 1. So remember, an plus 1 is a1 plus a2 plus up to an plus 1. Partial n plus 1 is partial 1 plus partial 2 plus up to partial n plus 1. Okay, and 22, now I'm defining a third one then, is an plus 1 partial n plus 1. And then you have this relationship. The whole idea of these ideas is to relate it back to the standard gradient operator. Okay, now I'm doing calculations, which can be very confusing. I won't even try talking about them. I have checked them, they are correct. So let's go down. I won't talk about that. Again, I'm just squaring these things. These look, again, remember these are vector operators, so that's nothing unusual about, but working out what these things come out as becomes complicated. Okay, so maybe I won't try talking about that. Go down a little further. Okay, this is interesting. This is not so hard to understand. So I'm just taking, remember that means the sum, partial 1 up to partial n plus 1 squared. You square it all out, you get this relationship. Again, that's all the binomial terms. So you can relate to that because, as you can see, that's just the sum of a binomial. Partial 1 plus partial 2 plus partial n plus 1 squared. So that's a way of writing that partial sum. Remember, partial derivatives commute. So we can write that as there are n plus 1 times n over 2 terms of this thing. It's like a determinant expansion, really. Another way of writing a determinant expansion. Well, again, so it's very interesting insofar as that involves a binomial expansion, which is understandable. Everyone knows about binomial expansions relating to these things. Okay, now here, again, I'm using the caret over the AI. So what does that mean? Well, that means I'm taking A1 plus A2, leaving out the AI. Whenever I use the caret over the AIs, it preserves, it's a vector. And okay, I'm taking the AI dot. That means take the sum of the AIs, leaving out I, take the sum of the AJs, leaving out J's, take their inner product, you get that inner product. That becomes important to understanding these relationships. Okay, now I try to define this directional sum. I'm trying to work out these formulas in a way that's understandable. Well, let's go down. You can, okay, so go down. We'll have to skip those things, but I want to relate it to the standard gradient operator okay, here it is. Look at this relationship. Go down a little, 24. Look at 24, equation 24. Go down a little bit.
34?
24.
Oh.
24. Yeah, it's covered by your picture. I can't go down a little bit. I can see it better. Can you go down a little more? I'm going the wrong way.
24 is back here.
Yeah. Okay. Yeah. 24. That's what I want. Okay. Go up one more. One more up. Right here. No, that's not what I want either. Go down. You have to go down, I guess. I'm sorry. Go down. Go down. Okay, this one, 34. I'm sorry. It was 34. I couldn't see it. Yeah, 34. So that's the standard gradient operator now. And I'm relating that standard gradient operator to the hat and caret gradient operators. Okay, so expressed in terms of the hat operator, it comes out like this. I don't prove these formulas because actually what needs to be done really is getting a Mathematica program working in terms of table 1 and developing these, so you don't have to do these things by hand because they become extremely, you make mistakes, at least I make mistakes all over the place. And it's extreme, then I have to recheck. I hope these formulas are correct. I believe they are. I've checked them for certain values, but for example, we know that the two properties, 1 and 2, that I defined the standard gradient operator for, must hold true with these relationships. The interesting thing about the hat gradient is that if you apply it to X, you get 0. Because remember, the hat gradient operator is just A1 partial X1, A1 partial X2, and so on. So if you take it to the position vector, the hat gradient gives you 0 because it gives you A1 times A1 plus A2 times A2, and they're all zeros. On the other hand, the caret gradient is related to the standard gradient by this relationship then. Okay, looks like a mistake. No, I guess that's correct. Yeah, okay, these, I think these are the correct formulas. And then, okay, the idea, yeah, these are correct. I've checked this stuff. Now you look at the Laplacian, it becomes interesting because as you know, Laplacian is used to define all kinds of things, electromagnetic fields and quantum mechanical relationships. Laplacian is very important. So I spent a lot of time, but it looks to me like I'm getting some new relationships between Laplacian usually Laplacian is usually represented in terms of, what is it, the D'Alembertian, I guess it's called in space-time algebra and in Dirac algebra. What's the Laplacian called in the Dirac algebra? Is that called a D'Alembertian? I can't remember exactly.
Yeah, sounds right to me, yes.
Okay, so that's what this gradient operator represents here, and I'm getting a new factorization of it. Okay, so it becomes okay, this relation, let's see, maybe is this the one I want? Okay, that's a general relation. Let's go down a little further. You can see what it looks like in space-time then. Okay, here, that's 36 and 37 are interesting because they're related to, okay, that's the general formula which follows from that earlier formula. So Laplacian becomes, you can factor it into a product of one-dimensional. Well, remember the partial sum is a scalar operator. So the sum of partial scalars, and that's the hat gradient, which is simple. It's one of the simpler ones to work with because it's just A1 partial x1 plus A2 partial x2. And the interesting thing is that hat gradient applied to the position vector is 0, which is nice. So that's why in developing these formulas, it's easier to express this standard gradient operator in terms of the hat, these other hat and caret gradients. Okay, in space-time, if you go down one more down, you can see, well, this is space-time, the Dirac algebra. So this gives I've never seen this relationship in the Dirac algebra, but it should be interesting. I don't think there's any mistakes here. I need to check more of these formulas out. But again, I need to develop in Mathematica something to handle efficiently that table 1. Because remember, all these things are really defined in terms of that basic table 1, plus the idea of Grossman algebra. And that's it. So it's independent of matrices in a way. You don't need matrices if you develop in this way, but it seems to give new relationships. For example, I think this relationship 38 and 37 or 36 of the more general formula will give you new solutions. What I call opens the door to a new class of solutions of the Laplace equation in the geometric algebra G 1 comma n. And I give some references to some of the other papers that where the gradient operators discussed there. Okay. Okay, the last section is interesting because it relates, I try to relate it more to, Hesnes is, I think one of the most important ideas that Hesnes developed was his idea of a splitting of the Dirac algebra into the even subalgebra. The even subalgebra of the Dirac algebra gives you the reference frames of relativistic observers. So this is extremely important that in the way you find, which I've developed, idea in an inertial system with a vector and a bivector in one inertial system, or for example, what's called an electric field inertial system, if you look at it from another observer moving with respect to that observer, it becomes a mixture of a vector and a bivector. So in other words, what's a vector in one inertial system is a mixture of a vector and a bivector in another inertial system. But so again, that emphasizes the idea that the distinction between a vector and a bivector is not really so important. And that's, of course, where I will criticize what you mean by a covector. A covector is a separate space from vectors. And that's an arbitrary distinction, which really is not necessary and which covers over these other interesting ideas, which I think are missing in which are possible to develop when you choose, for example, a base of null vectors, A1 up to AN plus 1, as I've done. But again, there's just so much to do to try to see where this goes that I don't know how much more I'll be able to do, but I hope that people will pick it up and see it as being interesting, or at least relegated to the graveyard if that's where it belongs. But I think there are, to me, it's held my attention for a long time now. I've struggled with to make any progress at all. It seems like, for example, finding that canonical definition to make all these inner products equal to 1/2 was in itself very difficult, which I didn't get until, I don't know, 3 or 4 months ago. I think in January, when I was in Mexico the last time, I finally found out how to define these nilpotents all equal to 1/2. At first, I thought maybe it was impossible. Anyway, that's another story, of course. But anyway, so I guess I don't really have much more to say. I don't know how much time maybe Jesus wanted to talk about some ideas that, or maybe Bill wants to, or maybe there's no time. I can't really see the time.
Well, it's currently, let me just check here.
I think that maybe it is better to the next session. I can present something about. I stay working with the category theory, and then I am, in fact, now in the concepts of duality. Then I think it can be interesting to connect with this presentation, but I prefer maybe to the next session for.
Yeah. Of course, I neglected graph theory in this one, because I did emphasize that, we have n+1 things taken 2 at a time, which exactly why I started thinking that this must be related to graph theory. I still think that you can do something with those ideas, but I'd like to hear what you have to say more about the graph theory aspects. I think it is closely related to graph theory, maybe not exactly the way I think it is, but I think it has possibilities.
Yes.
I want to talk about that Euclidean structure that arises. Maybe look at definition 42. Can you look at definition 42 there? That's where the
yes,
here in 42, I'm saying that the Euclidean inner product arises. You don't change the structure of the Grossman algebra at all. So a bivector, a k-vector is the same as in the usual Grassmann algebra, but you just change the metric. You give this new definition of the metric, which follows from the previous 40 and 39, or 41 and 40, and you get a whole new structure. And somehow I believe that this might be the distinction between a particle interpretation and a wave interpretation. And that's what I give in that figure. Maybe you want to go to that figure. I give a figure on where is
before we move on. Can I just ask about this notation here? You have why do you have a star like this?
Oh, that's because I've changed the inner product, the definition of the inner product. So I'm saying keep bivectors, keep the gradient, the Grassmann algebra part of the algebra. Don't change that, but just change the inner product a little bit by introducing this new inner product. It's down 42, I guess it is. Go down a little bit more. Can you go down a little bit?
Yeah, but still, I'm still
40.
a bit confused.
Okay, right here, 2. That defines a new inner product of two vectors. Instead of using v dot w, that's in the usual Grossman Clifford algebra G1n. Instead of keep bivectors, k vectors the same, but introduce this new inner product 42, you get this star geometric algebra, which is of Euclidean space En plus 1 of the observer. Well, the observer, when he's making magnetic fields, he uses the left side of that figure I give. But for quantum mechanical side, I use the right side of the Euclidean space of the observer to define the quantum mechanical aspects. Well, that's the idea. Maybe it's not valid. But where's my figure? My figure is on, can you find the figure where that is? Maybe it's before.
Here.
Oh, right here. Yeah, that's the figure. So with that new metric, that's what I call G star. And I think I'm trying to interpret the wave mechanics on the left side in this Euclidean algebra defined by the gamma zero of an observer. Remember, in Hesseny's splitting of space-time, each observer, you take the even subalgebra. That's what I denoted by, it doesn't come out. Yeah, the even subalgebra of G1n plus. That means the even subalgebra. Find observer, the polyalgebra, which is the algebra of the observer. On the other hand, using this notation, you find that you get, if you perturb the metric just a little bit, you get the Euclidean space structure. And that's, I interpret as being the quantum mechanical, because when a particle is entangled, there is no metric involved. Well, you can think about as being Euclidean space of the observer, because that's really used to, as I believe, to develop the quantum mechanical aspects or wave splitting aspects. So on one side, the geometric algebra 1n, but then of an observer, the even subalgebra, but for the wave mechanical side, well, anyway, I can't really say too much more about it than what I have in the text. So, but I think it is interesting ideas. You can see how they arise. Again, I'm sorry about the notation. I couldn't do any better at this stage. And I tried to be as clear as I could be, but again, the notation is difficult. In fact, I felt I had to develop a new notation because I just couldn't write the stuff down that I had to write down. So anyway.
For me, this seems like requires maybe another presentation.
Okay, well, I can try working, like I want to develop a Mathematica program. Maybe I'll work on that this next, to the next time, because I like to check more things too. I need more, it'd be nice to develop the tools to handle this without having to do hand calculations that are almost impossible. But this is interesting how this inner product arises. And I believe it's correct. I need it, how this, by perturbing the metric, you get a Euclidean structure. So that means picking out, remember now, picking out the first two vectors, what I call the seed. That's what I call the seeds, E1 and F1. And then you can randomly pick out all the other ones to define the whole geometric algebra G1n. Yeah, that's what I called it, seeds. So picking out the first two, then all the rest are defined in terms of going up canonically by that relationship for the alpha K. Okay. Anyway, so that's the best I can do right now, I guess. So I interrupted Jesus. So maybe Jesus wanted to say a couple more words about his, what he, or whatever. It's probably time to end, I suppose.
Yes. So, Jesus, you suggested that in 3 weeks' time, you could give us a presentation about focus more on category theory and duality.
Yes, yes, yes. And the idea is to continue with some general concepts in category theory, but in fact, um, emphasizing the concept of duality and how we can use this in graph theory, consider this like a category. The idea is that with this approach, we can now go back to the first idea of representing algebras with the graph theory. Then this is my idea about the presentations in the next session.
Okay. Yes, I think,
Yeah, I mean,
that's interesting.
I wonder if there'd be any category way of representing this, this new duality relationship I'm giving it. How would that look in category theory? That's all.
Oh, sorry, I lost your comment.
I was just wondering whether you can represent in category theory my concept of duality, or this uh, correlated nilpotence. This relationship J plus AJAI equal to 1. As a, how would you, could you say something about that in category theory? What's that doing? Category.
Okay, I can try to review the idea and how this can be expressed in terms of category theory. Mhm. Okay.
Okay. Well, I think it was an interesting session for sure. And I look forward perhaps at some point in the future of revisiting this this presentation by Dr. Sobczyk, especially focusing on this issue of Euclidean geometry within this same structure. For me, I think that would answer some questions that I had perhaps at the beginning of starting to read this paper. I thought, it's much more normal to, in a sense, to start with the discussion of Euclidean geometry and then to think about Minkowski space as somehow a modification of the Euclidean geometry, but this presentation seems to turn that around.
Now the vector derivative is really what I was doing in Euclidean space all the time. Now actually it's a concept that can be like anything.
There seems to be some problem with your audio, Dr. Sobczyk. I couldn't hear your last
I was
thing.
covering up.
It is better
maybe I was
when
covering.
you apart from your phone, because if you go very near, then we lost your comment.
Yeah, I was covering up the microphone. I think that was the reason. So
okay, now it's better.
Yeah. So what was I even saying?
So my comment was just that your presentation here seems to invert the usual sort of conceptual development that you would start with. In the past, people would start defining what they mean by Euclidean geometry, and then think about hyperbolic geometry. Yeah. later.
That was my comment, actually. When I did my thesis, I was actually only using the Euclidean geometry aspects. But now in developing these, I see the metric really is not important. You can use any metric and it's the same. So that's exactly what covectors are doing too. I believe covector spaces are just really introducing the structure in a different way, that's all. But maybe it's covering up some of these ideas in this symmetric approach in the same algebra that I'm trying to do now with this Minkowski Lorentz space
Okay,
or any other
Well,
metric.
all right. Well, let's agree. We'll meet again in 3 weeks' time, and Dr. Cruz will give the main presentation. If there are additional comments you'd like to make, Dr. Sobczyk, at that time about developments in this theory that you presented today, I think we certainly could make a bit of time to
Okay, I appreciate
review
that.
that. But we could start with the presentation by Dr. Cruz and go from there.
Well, thank you very
Okay.
much for
Mhm.
flipping through this with me because I'm a little bit limited what I can do. I guess the power has gone back on here.
So just in
but-
time for our meeting to be over, now the power is available.
Well, thank you very much for helping me out there.
Okay, no problem. So see you both again in 3 weeks.
Okay.
Okay,
I'm looking
thanks a
forward
lot. Bye.
Okay, bye for
Yeah,
now.
have a good, bye.